Okay, good morning, all of you. Thanks for coming. Um, so, just a reminder of what we have covered in the previous two classes. Well, the class before yesterday, we talked about the eigenvalues of angular momentum operator, and I also introduced you to the idea that angular momentum is the generator of rotations. Now, to provide a bit more background for that, one needs to talk about symmetries in group theory. So yesterday I started talking about symmetry group theory, and I gave you this example of the group of symmetries of a square. One can similarly consider the group of symmetries of any polygon, for example. One can consider the group of symmetries of a triangle, that is called the dihedral group. And now groups are abstract objects, right? And the elements of a group satisfy something which is known as a group multiplication table, which looks like this. Okay. And a group satisfies three axioms. The first axiom is closure under group multiplication. So if I take the product of any two elements, I get an element of the group again. The second one is the existence of the identity element. So that means there is always something which I can consider to be the number one. Okay. And then finally, the existence of an inverse. That means there is always some group element such that if I multiply that by its inverse, I get the identity. Okay. Now, the group multiplication does not need to be commutative. Okay. When it is commutative, when for example, AB is equal to BA, that it is called an abelian group. And when AB is not equal to BA, then it is called a non-abelian group. Okay. Now, groups are abstract system, abstract objects, and so we cannot say that an element of a group is a matrix, this object or that object. Okay. Instead, what we say, we have to specify two things. We have to specify the vector space. Generally, we think of a vector space on which the group acts. Okay, so we think of group elements as transformations. So they act on a vector space and they take elements of that vector space to other elements of the vector space, right? So as an example, you can consider the vector space of all vectors in two dimensions, right? X, Y. So in that case, you can ask, well, what are the transformations which act on these vectors, right? Well, this is a two-dimensional vector space. So the transformations will be 2 by 2 matrices, right? Now these 2 by 2 matrices can be, in general, they can have arbitrary components, right? So if you don't fix the components to be, let's say, cosine or sine or something like that, then you get a group which is called, so if you have the group of 2 by 2 real valued matrices, okay, is called GL. Instead of 2 by 2, I can say n by n, NR, right? Where the G stands for general, L stands for linear, and N tells you the dimensionality of the matrices, rank of the matrices, and R tells you that the elements are real valued. Okay. So now, and then if we restrict to, let's say, the group of so if we have for n is equal to 2, right? We have this thing. If we take an element of GL2R, then we can write this G as a matrix, right? Where A, B, C, D, where A, B, C, and D belong to R, right? And the only restriction is that elements of the group must have an inverse, right? The group of n by n real valued my network is being a little invertible means that determinant is not equal to 0, right? So if the determinant is 0, you cannot find an inverse of the matrix. So the only requirement here is that det G is not equal to 0, which means that G inverse exists. Okay. So this is the GL2R. Okay. And now another example of a group, a simple example of a group is, let's say you consider real numbers. Okay, does this form a group? Does the set of all real numbers form a group? Anybody? First of all,
yes, sir.
Can you define a group multiplication operation? Now, this is the thing to realize, right? That the group multiplication is an abstract operation, right? So it doesn't have to correspond to the multiplication as you understand it as multiplication of numbers, right? So for example, we can take plus as the group multiplication. Okay. So then you can see that A plus B also belongs to R, right? For all A, there exists A inverse. What is the inverse of A under this operation? Minus A, right? Just the negative value of A. And so we can take plus as the group multiplication. And what is the identity? What is the identity element?
0.
Identity element is 0, right? So real numbers form a group, right? They are closed under group multiplication. There is an inverse, there's an identity, right? Now, the set of real numbers has more structure than just being a group, right? It can also be written as a vector space, for example, or what you call an algebra. But is the sound of traffic in the background, is that audible?
Yes, sir.
Yes, sir.
Is it too loud?
No, sir.
Okay. So similarly, alternatively, one can take as your group operation. Let's just call it the group operation rather than calling it the group multiplication, right? Then A times B belongs to R, right? A inverse is equal to 1 by A, right? And identity is what? Is equal to the number 1. right? So again, the real numbers forms a group. So it forms a group in different ways, right? So a set can be, actually, let me close this windows because okay, that's better. 1 second. So now, then yesterday I gave you another example of a group, which was U1, right? So this is the group of all complex numbers with amplitude 1, right? So basically e to the I theta. So you can check that if you have e to the I alpha, e to the I beta is equal to e to the I alpha plus beta, which belongs to U1. E to the I alpha, e to the minus I alpha is equal to 1. And 1, the number 1 is the identity. Similarly, for instance, you can ask about the group of integers. The group of integers form a group under addition, but they don't form a group under multiplication. Right? So this is U1. This now the thing is that this is one representation of U1, right? As I told you, this is the one-dimensional representation. What do we mean by one-dimensional? It means that well, let me give you the example of the two-dimensional representation. So U1 can also be written as these matrices: cosine theta, sine theta, minus sine theta, cosine theta. So here again, which I can write as r theta, let's say. So then the inverse of r theta is what? R of minus theta, right? Identity is just the identity matrix, 2 by 2 identity matrix, right? And multiplication is just the this is something that you should check. Right? So you should take two of these matrices, multiply it, and then use some trigonometric identities to show that it is equal to R alpha plus beta. Okay. Now, so when we have a group, what we say is that the group acts on some vector space. Let's say V. My internet is being stupid again. 1 second. Let me switch to.
Hello, sir.
Yeah.
So this rotation matrix in 2D is commutative, but in 3D, sir, it. Hello.
Okay. I'm back. Can you hear me? Okay, it's updating.
Yes,
that's better. Okay. So the group acts on a vector space V. All right. And what is the action of a group? It's given by some matrices, right? So the group action is given by a matrix, right? So now if the dimension of the vector space is equal to n, then the dimension of these group matrices is n by n, right? Right, okay. Now, if you look at this group, r theta, right? If you look at U1, now this U1, this representation of U1 in terms of 2 by 2 matrices, right? R theta, this is a subset. These matrices, they belong to this GL2R, right? What is GL2R? GL2R is just the space of 2 by 2 matrices, right? And you can confirm space of 2 by 2 invertible matrices, and you can confirm that these matrices form a group, right? And so R theta is a element of GL2R, right? Sorry, my network is being horrible today. I don't know what the problem is. Okay, problem is that basically we have too many people with too many devices on the same router. That is, I think, the problem. Okay, so we have these matrices R theta, then element of G2, GL2R, right? But all GL2R matrices, the set of GL2R matrices is bigger than this set R theta, right? So we will say that this group U1 is a subset of GL2R, right? These matrices over here, they are a subset of the set of all 2 by 2 invertible matrices with real number, right? And these matrices, so instead of U1, I should write this as SO2, okay? Now I'll explain what this SO2 means, okay? So what is SO2? S means special, O means orthogonal, okay? And 2 is just 2 by 2, okay? What is the meaning of special and orthogonal? So a matrix is called orthogonal if the transpose is equal to the inverse, right? Now, if you look at this matrix, this matrix, you can see that if you take the inverse, if you take the transpose, then here you get minus sine theta, and here you get sine theta, right? That's just the transpose, and that is equal to r of minus theta. So the transpose is equal to the inverse. Special means that the determinant of A is equal to 1. Okay, and you can see that the determinant of A here, what is the determinant? It's cosine square plus sine square, which is 1. Right? On A, by comparison, in contrast, the group of this GL2R, the group of 2 by 2 matrices, these matrices, they do not need to be orthogonal, right? There is no restriction on that. And they don't need to be special, right? There is no restriction on what value that their determinant can take, except that it should not be 0. Okay. So this is why we refer to this as SO2. Okay. Now, in a similar manner, one can define SO3. What is SO3? It is a group of 3 by 3 orthogonal matrices with unit determinant. Okay. Right? By the same we are using the same labeling, right? Now, what is SO2? SO2 is the group of rotations in 2 dimensions. Right? SO2 is the group of rotations in 2 dimensions, right? As I explained in the class yesterday, right? So if you have a vector, one second, I'll be right back. I have to go and scold my family members and tell them not to use the internet.
Sir, Mike.
It takes any vector and rotates it to another vector in the plane, right? Now, similarly, SO3 is the group of rotations in 3 dimensions. Okay, so SO3 takes any vector in 3 dimensions and it rotates it by now this will call alpha. So this R alpha beta gamma is an element of SO3. Now for SO2, we only needed one parameter, which is theta, right? There are 3 parameters. Okay, why is that? Because when you think about rotations, in 2D, there is only one independent rotation, right? So for example, you can call it in XY plane, right? Whatever you want to call your plane, you can call it anything you like. But if you say it's X and Y, then you have one rotation, that is the rotation in the XY plane. In 3D, you have rotations in XY plane, YZ plane, and ZX plane, right? So you have three independent rotations. So that's why you have three independent parameters. This is also comes, so another way to look at it is that you have this parameterization of three-dimensional rotations in terms of Euler angles. So this parameterization, it's a little bit technical. I mean, it's not very complicated. I can explain it to you, but it will not make any much difference going into the details. So the point is that these group elements, they are described by three numbers. You can think of these three numbers. So one is rotation around XY, rotation around in YZ, this, and then this, right? So you have three different planes. You have one plane, you have two planes, you have three planes, three orthogonal planes. So you can have rotations in either one of those planes, right? Now, why are we talking about rotations? Because we are talking about angular momentum. And I've said that angular momentum is the generator of rotations, right? So what does it mean to say that something is the generator of something else? Okay. So one example is that linear momentum is the generator of translations, right? Okay. So what that means is that if you take exponent of something like minus I by h bar delta x times p hat, and you act on some function of x, what does this give you? This gives you f of x plus delta x, right? So this is what we used to say that p is the generator of translations, right? I should say p of x. So similarly, if you take now for rotation, we have what are the operators for angular momentum? Lx, Ly, Ly, and Lz, right? So similarly, if you take this thing, let's say Lx, and you exponentiate it in this manner, okay, what will you get? You will get a matrix. Okay, why will you get a matrix? Because this Lx is also a matrix, right? So when you exponentiate this, you will get a matrix, and this matrix will, when you act on a vector, what this matrix will do is it will rotate that vector. Okay, so let me explain how that happens. Okay. Okay. And now instead of L of X, let me call this something else. Let me call it J of X. I'll tell you why. Yeah, let me call it J of X. Okay. So what is this J of X? What is this exponential give me? So if I exponentiate this, I get if I expand this exponential, I get identity matrix. That's the 0th order term. Then I get minus I by h bar delta theta jx. Then we have the higher order terms, right? The higher order terms are you'll get a I square, which is minus 1 minus delta theta square by h bar square jx square, right? And then plus I delta theta cubed h bar cubed jx cubed, and so on. Now, in this expansion, one of the things that you can notice is that every alternate term, right? Every alternate term in this series is imaginary. These are the complex terms. Right? They all have a factor of I. On the other hand, if you look at these terms are real. Right? So what I can do is I can collect my real terms and my imaginary terms. Like this, and you will get something like this. Delta theta cubed jx cubed, right? Minus so on. This will be the real part, and then you will get an imaginary part. Now the imaginary part will be minus.
The part will contain the even powers of delta theta.
That's right. So this will be square, and this will be 1 square. This will be 4. Sorry. So the imaginary part will contain delta theta by h bar jx delta theta by h bar cubed jx cubed plus, and so on. So this is the imaginary part and the real part, right? Now you can see that this sort of resembles the expansion of sine and cosine, which is not surprising, right? Because we are taking the expansion of exponential of something, and you know from Euler's formula that exponential e to the I theta is cosine theta plus I sine theta, right? But now in this case, Jx is a matrix. Okay. So let's ask, what is this? What is Jx? Let me tell you what Jx is in terms of matrices. So 1 second again. I really should remember this, but I forget my matrix representations from time to time. Okay, so Jx will be right 0 0 0 0 0 right 0 minus 1 0. Okay, this is what Jx is, and I'll explain to you what this means. where this expression comes from in a minute. Right, but for the time being, let us see what happens when I substitute this expression in this expansion. Now we have to ask what is jx square, what is jx cube, jx4, and so on. Okay. So if I take jx square, what will I get? Well, you can see that this matrix is block diagonal, right? So I just have to take the square of this part. So what happens when I take the square of this part, right? I get -1, 0, this time 0, and I get -1, right? So I get minus the identity matrix. So I'll get 0, 0, 0, 0, 0, -1, 0, 0, -1. Okay. Then what about jx cubed? Right? Jx cubed, again, it will be this matrix multiplied by this matrix, right? All the other terms will be 0. 0, 0, 0, 0, 0, 0, 1, -1, 0. Right? The only thing that will happen is that the sign of this will change, and jx4, what will it give me? It will give me 0, 0, 0, 0, 1, 0, 0, 0, 1. It will give me the identity matrix again. Then these matrices will repeat. Do you guys have a class just now?
No, sir.
नहीं, लोग जा रहे हैं ना, तो लोगों को या तो बोरिंग लग रहा होगा या समझ में नहीं आ रहा होगा, या फिर क्लास होगी, इसलिए मैंने सोचा। ठीक है, जो भी है। So now this keeps repeating, right? So jx cube is equal to minus jx, right? And jx to the fourth power is equal to minus jx squared. So you can write out all these terms in this way, right? This is identity. This is jx. So jx squared is this matrix. Then jx fourth is again minus jx squared, and so on. Okay. So right. So then what happens is, when you insert all of this into this expansion, into this series and into this series, what you get is something like this. You get, let me just write out the final answer. You will get 1, 0, 0, 0, cosine theta, sine theta, 0, minus sine theta, cosine theta. Okay. So now what is going on here? Where are the cosine terms? The cosine terms are coming from these jx squares, right? From jx square and jx4. And then you have these sine terms, they are coming from the even powers of j. Okay. And so what I'm saying is that this exponent of minus I by h bar, instead of delta theta, I'm just writing theta, is equal to this expression. Now what is this matrix represent? This matrix represents a rotation around the x-axis, or we should say in the yz plane. In the yz plane by an angle theta. Right? These two are the yz components, and the x component doesn't change. So if you act on, so that's why I wrote, we can write it down as in this way, Rx theta. It means a rotation around the x-axis by an angle theta. So if you take Rx theta and you act on some vector x, y, z, what will you get? You will get x prime, y prime, and z prime, where x prime will be unchanged and y and z are related to each other by a rotation, by this rotation, cosine theta, sine theta, cosine theta, y and z. Okay. So this is what we mean when we say that this Jx is a generator of rotations. It is generating rotations around the x-axis. In a similar manner, I can write down what the generator of rotations around the z-axis is. This is going to be Jz is going to be, again, the identity, nothing will happen here. So this will be 0, 0, 0, and you will get 0. And the same thing, minus 1 here and 1 here and 0. Sorry. This is the generator of rotations around the z-axis. And similarly, you can figure out what Jy will be, right? Now, where do I get this expression from? Like if I want to go in the reverse direction, how can I determine this? Okay, so let me look at right. This is 5. So let me look at Jx. Let me look at, sorry, Rx theta. So the full matrix Rx theta is 0, 0, cosine theta, sine theta, minus sine theta, cosine theta. Okay. Now let me ask, what happens when theta is equal to very small number, when theta is much less than 1? What is the expression for Rx theta? Rx theta can be written as 1, 0, 0, 0. What is the expression for cosine when theta is very small? It is approximately 1.
1.
For sine theta, it is 1 minus theta, 0, minus 1 plus theta, and cosine theta is again 1. Oh, sorry, this is not 1 minus theta, this is theta, right? Sorry, this is theta and this is minus theta. Okay. So now if you look at this expression, you can see that it can be written as the identity matrix, which is these 3 numbers, plus theta multiplied by this matrix 0, 0, 0, multiplied by this matrix basically. If you take this J of x with minus 1 and 1, and this theta, you put minus sign here. So let me again shift this all down a little bit. Okay, so you put minus theta and then 0 and then minus 1, 0, 1, 0. This is R of x. Theta, for theta is a small number, right? And what is this? This can be written as this identity minus theta times Jx. Right? That is what we have defined Jx to be, right? This quantity. Now, what is this expression? This expression is approximately, it's equal to the first term in the exponential expansion, right? So if you write down an exponential of minus theta times jx like this, if you look at this exponential, what will you get? You'll get 1 minus theta jx, right? Plus order theta square, order of theta square and higher terms, right? So so if you want to generate an infinitesimal rotation around the x-axis, what do? You take the unit, the identity, and you add this component. So that is why this jx is called the generator of rotations around the x-axis, because it generates a very small rotation. Now, what if you want to generate an arbitrary rotation, a big rotation, not an infinitesimal rotation? What will you do? You will simply multiply Rx theta for very small theta by itself, right? So you will multiply, so that what you are doing essentially is,
Sir, can you repeat this?
Yeah, 1 second. Repeat which part? Sorry.
सर बस जो अभी पीछे आपने बोला, ये जो स्टेटमेंट बोला कि
Generator के बारे
yes
में.
yes sir, yes.
हाँ, so this is called the generator because you can use this to perform infinitesimal rotations around the x-axis. So what is an infinitesimal rotation? It is identity, right, plus this quantity. Theta is the infinitesimal parameter and jx is this matrix. Okay, and I think the factors of h bar are probably not needed. So, and I'm missing a factor of I somewhere in my definition of jx. So I should probably be a little bit more careful about these things. So I should put something like, instead of -1 and 1, I should put I and minus I, and then this thing will become minus I theta times jx. And then I'll put a I over here. So the definition of jx should have an imaginary factor. I think so. Okay. Anyway, those things can be fixed, not a problem. The main thing is that if I want to create, if I have an infinitesimal, so let me write it like this. Rx delta theta is equal to the identity minus I delta theta jx, where delta theta is much less than 1. Now, if I want to generate a finite rotation, what is a finite rotation? A finite rotation is by some angle theta, then let me take theta and let me divide it up into n pieces, where n is some number which is much larger than 1. So this means that delta theta will be something much less than 1. Okay. Then I take Rx delta theta to the nth power, right? What will this give me? This will give me Rx delta theta each time, right? It will add. Why will it add? Because remember, when you multiply one Rx with another Rx, nothing is happening in the Z direction. It's only in the Y, nothing is happening in the X plane, X direction, only in the YZ plane. So it is, the rotations are additive when you're looking only at one plane. So Rx delta theta, and if you look at this, what is this? This will give you Rx times n delta theta, and delta theta is equal to theta by n Rx theta, right? So if you want to generate rotations around by some finite amount, what you do is you divide it up into rotations by some small steps. Okay. So this is the reason. So this is the generator of rotations in the x direction. In a similar way, you can define the generator of rotations in the y direction and the z direction. Okay. And now, so you have three matrices now: Jx, Jy, and Jz. All right. And now these matrices, they probably class is going on. बंद कर दरवाजा. Close the door. Okay. Now these matrices, they have some important properties. One of the properties is that they don't commute with each other. So if you ask what is this Jx and Jy, what is the commutator of Jx and Jy, then that will be proportional to Jz. Okay. And similarly for Jy, Jz, you will get Jx, Jz, Jx, you will get Jy. So this is because rotations around, or I should say rotations in different planes, they don't commute. Okay, what does this mean? Take a simple example. Okay, let's say you take your cell phone. Okay, you start off with your cell phone in some orientation like this. Okay, now I have three different axes. What are those three axes? Let me say this is my z, this is my y axis. Okay, like this. This is my y axis. This is my x axis, and this is my z axis. Right? Now you imagine rotating this first around the z axis by 90 degrees. Okay. So I rotate it by 90 degrees around the z axis. Okay. Then I rotate it by 90 degrees around the x axis. Now x axis is what? This one. So I rotate it by 90 degrees around the x axis. Okay. So it ends up in this orientation. Okay. Now keep in mind what orientation this is. Now let me start from the beginning again. This time, first I rotate around the x-axis by 90. So I rotate by 90 degrees around the x-axis. Okay, this is what I get. Now I rotate by 90 degrees around the z-axis. Z-axis is this one. So I rotate by 90 degrees around the z-axis. I get this. Right? Is this the same as the previous orientation? No. Right?
No, sir.
Earlier, the previous orientation was this, I believe, right? And now I'm ending up with this. So rotations don't commute with each other. On the other hand, if you look at translations, right? If I look at translations, so translations are very easy. If I take this object and I translate it by this amount here, or I translate it by this amount in this way, I end up at the same point, right? So translations are commutative, but rotations are non-commutative. Okay. So we have the group of rotations, which is the group of SO3 matrices. This group has the generators. We have a set of 3 matrices, JX, JY, and JZ. All right. Now, what does all of this have to do with quantum mechanics? Where does quantum mechanics fit into this picture? Okay. Well, we are talking about angular momentum. We are talking about a particle that has some angular momentum pointing in some direction, right? So now let's say that you have a particle, a classical particle, and it has some angular momentum. So this is a classical particle, right? Now this angular momentum is a vector, right? It is just 3 numbers, Lx, Ly, and Lz. And so what is the relation between this and the group of rotations? The relation can be understood as follows. If I write down the wave function for this system, for this classical system, so the wave function will be some state. Okay, I'm also getting confused. Actually, I'll stop here, okay, because I've already made too many small errors. So we'll continue in the next class. We'll continue in the next class as to what the relation of all this is with quantum mechanics. So you should go and read up in Sakurai in section 3.1. Okay, and maybe Sakurai's treatment is not that good. So if you don't like Sakurai, you can always refer to any other book like Shankar or Griffiths or anything else. Okay, whatever you find convenient. But this you should understand. I think another one good reference is simply you can look at Wikipedia. If you say generator of rotations, for instance, so I'll show you how, let's see, share screen. And, okay, so if you just say generator of rotations in Google, right, you get rotation operator. And okay, now, okay, so this is again not that, again, yeah, this is not that simple to understand if you're just starting out. So you can look at something, let's say stack exchange. Stack exchange, I hope everybody knows what stack exchange is.
Yes, sir.
Right? And so you can see what this person is asking. I have been looking all across the internet and every book I find trying to get a full derivation for the generator of rotations. Okay. So I tried finding the generator of rotations, but there comes at a point at which almost all sources I have read define the generator. right? For example, Sakurai states that this is the generator. I would like a derivation. Now the derivation is very straightforward, right? As I said, you look at the finite rotation and you look at the what happens when you take the infinitesimal part of the finite rotation, right? So anyway, this answer maybe is again very complicated. So I don't know if I would go and read that answer, but I would just say that the generator is simply that infinitesimal element. Okay. All right. Now let's see what is this presentation. So this is the document I just downloaded. Some about rotations. Starts off with talking about rotations in 2 dimensions, which is useful, right? All of these things that I've already talked about, only with a minus sign is a little different. And then he talks about this U1 component, right? Then rotations in 3 dimensions, right? So this is what I've already explained to you, that if you take any rotation around the same axis, it can be written as a sum of rotations around that axis. And then he talks about how you take rotations in the state space. So this I'll talk about tomorrow. This I'll explain tomorrow. So you can try reading through this. I don't know if reading through this will necessarily be very enlightening, but you can try. Okay, so I'll stop here. So I'm guessing there are not too many questions because you have to sit down and work through all of them. So I'll give you some problems tomorrow.
Sir, can you please share this PDF?
Yeah, no, I will. That's why I downloaded it, right? To find something that is pedagogical. Okay, or maybe I'll make some notes of my own. I'll see and share those with you. So ultimately what we want to understand is what is the relation between these matrices that we have defined, right? We are calling this a generator of rotations, and the angular momentum operator. Now you remember the angular momentum operator we defined as R cross P, right? So we want to ask, is there any relation between these two things? Is there any relation between the generator of these rotation matrices and this that x dou y minus y dou x, those operators? And we will see that they are basically the same thing in a different language. So that we'll see in the tomorrow's class. Okay. All right. Any questions? Okay. So I'll see you all tomorrow then.